Have you ever wondered what recursion is and why it's so important in programming? Imagine a mirror reflecting another mirror, creating an infinite series of reflections. This is recursion in a nutshell, a function that calls itself, creating a similar yet smaller problem to solve over and over again until it reaches a stopping point. This is a powerful technique in programming, utilized in everything from tree traversal to dynamic programming. It's like a set of Russian nesting dolls, each problem containing a smaller one inside, until we reach the smallest doll, the base case that stops the recursion. This way, big, complex problems are broken down into manageable parts. But be careful, without the right conditions, recursion could run indefinitely, like a mirror reflecting a mirror into infinity. By the end of this video, you'll have a clear understanding of what recursion is and how it works. Let's dive into the basics of recursion. It's a programming technique where a function calls itself to solve smaller instances of the same problem. Recursion is like a Russian doll. You open one doll and you find another one inside. You open that one and you find another, and so on until you reach the smallest doll. There are two fundamental components to recursion. The first is the base case. This is the condition that halts the recursive calls. Without a base case, the recursion would continue indefinitely, spiraling into a stack overflow. It's like reaching the smallest doll in our Russian doll analogy. The second component is the recursive case. This is where the function calls itself with modified arguments to progress towards the base case. Each recursive call should move the function closer to the base case, ensuring that the recursion will eventually stop. Let's illustrate this with the classic example of computing the factorial of a non-negative integer. The factorial of a number, say 5, is the product of all positive integers less than or equal to that number. So, the factorial of 5 is 5 times 4 times 3 times 2 times 1. In our recursive function to compute the factorial, the base case is when the number is 0. The factorial of 0 is 1. For the recursive case, we say that the factorial of a number n is n multiplied by the factorial of n minus 1. So the factorial of 5 is 5 times the factorial of 4. The factorial of 4 is 4 times the factorial of 3, and so on, until we reach our base case of 0. So in essence, recursion involves breaking down a problem into smaller instances that are similar to the original problem. Each recursive call operates on a smaller subset of the original problem, using the function call stack to manage multiple nested calls. Recursion is a powerful tool, capable of simplifying complex problems into manageable self-similar subproblems. But remember, it requires careful thought to ensure your base case is reached, to avoid an endless loop of recursion. Now that we've got the basics down, let's delve into the mechanics of how recursion works. At the heart of recursion, there's this key concept of self-similarity. This means that we're breaking down our problem into smaller chunks that are similar to the original problem. So when we call a function recursively, each call is essentially working on a smaller, more manageable piece of the problem. But how does the computer keep track of all these function calls? This is where the function call stack comes into play. Each time we make a recursive call, the computer adds a new frame to this stack. This frame holds all the information needed for that particular call, including the arguments passed to the function and the point to return to once the function call is complete. Now, this stacking process continues until we hit our base case. The base case is like the bottom of our stack. It's the condition that stops the recursion, the point at which we say, okay, we've broken this problem down enough, let's start building our solution. Once the base case is reached, the function stops making new recursive calls and starts to unwind the stack. Each frame is popped off the stack, and the return values are combined to form the final solution. This is why it's crucial that each recursive call moves us closer to the base case. If we don't make progress towards the base case, the function will keep calling itself indefinitely, leading to a stack overflow. So you see, recursion is this dance between breaking down the problem and building up the solution. It's a delicate balance, and getting it right can lead to some truly elegant code. But be warned, recursion is a powerful tool, but it can be tricky. Always ensure you have a base case that your function can reach. Otherwise, you could end up with a function that runs forever, consuming more and more memory until it crashes. Remember, without a base case to stop the recursion, the function would continue indefinitely, resulting in a stack overflow. You might be wondering, what's the catch with recursion? Well, there is a trade-off. Recursive algorithms can consume more memory than their iterative counterparts. The reason? Each recursive call requires a new frame to be pushed onto the function call stack, storing information such as local variables and return addresses. As we delve deeper into recursion, more and more frames pile on top of each other, each one demanding its share of memory. This overhead can become significant, especially in cases where the recursion depth is high or the function calls are particularly memory-intensive. It's like a stack of plates at a buffet. The more you take, the taller the stack, the more space it needs. But don't let this deter you. Despite the potential for increased memory usage, recursion often offers an elegant solution to many problems. Like a well-balanced meal, the key is understanding the ingredients and using them in moderation. So where can we use recursion? The answer is, in many places. Indeed, recursion is a versatile tool that shines in a variety of areas in programming. One of these is tree and graph traversal. When you're exploring nodes in a tree or a graph, you often need to visit a node and then explore all its adjacent nodes. With recursion, you can visit a node, then make recursive calls to explore the rest. The algorithm naturally follows the structure of the tree or graph, making the code clean and intuitive. In addition, recursion is the heart of many divide and conquer algorithms. These algorithms work by breaking down a problem into two or more subproblems of the same or related type, until these become simple enough to be solved directly. They then combine the solutions of the subproblems to solve the original problem. Classic examples of divide and conquer algorithms are merge sort and quicksort, which use recursion to sort halves and partitions of the array respectively. Recursion also finds its use in dynamic programming, a method for solving complex problems by breaking them down into simpler subproblems. It's especially effective when the subproblems overlap, meaning the same subproblem is used multiple times. In these cases, recursion can be used to break down the problem, and the results of each subproblem can be stored for future use, reducing the number of computations. But it's important to remember, with great power comes great responsibility. While recursion can simplify your code and make it more readable, it can also lead to problems if not implemented carefully. Always ensure your recursive function has a base case to prevent infinite recursion, and be aware of the memory implications of multiple function calls on the call stack. As you can see, recursion is a powerful tool that can simplify code and lead to efficient solutions. It's a testament to the beauty and elegance of programming, where a simple concept can lead to solutions for complex problems. So we've covered a lot of ground today on recursion. This powerful programming technique, where a function calls itself to solve smaller instances of the same problem, is like a magic trick that keeps on giving. It's an elegant tool that can simplify complex problems. But remember, like any magic trick, it requires practice and understanding to master. The two key components we've discussed are the base case and the recursive case. The base case is our safety net, the condition that stops the recursion from spiraling into an infinite loop. Without it, we'd have a runaway train of a function, speeding towards a stack overflow. The recursive case, on the other hand, is the engine that drives our function forward. It's where the function calls itself, but with a twist. Each call is a step closer to the base case, progressing towards the solution. We've also looked at the self-similarity nature of recursion. It's like a Russian doll. Each problem contains a smaller version of itself, waiting to be solved. This self-similarity is what makes recursion such a powerful tool for problems that can be broken down into smaller, similar subproblems. Now, let's not forget about the function call stack. This is where recursion shines, managing multiple nested calls, each one pushing a new stack frame onto the call stack until we hit that sweet base case. But remember, with great power comes great responsibility. Recursive algorithms can be memory hungry due to the overhead of these multiple function calls. So, always be mindful of the trade-offs. We've also explored some of the many applications of recursion, from tree and graph traversal, to divide and conquer algorithms, and even dynamic programming. These are just a few examples of the wide range of problems that recursion can tackle. Remember, recursion is like a loop in a mirror. It keeps reflecting until it sees the base case. With practice, you'll soon be able to harness the power of recursion in your own programming projects.